Now if you have an equation that is non-linear and in the same time non-separable, and you want to solve it using the exact differential equation approach, then in that case we can learn how to do that using a practical example. Now you have an example. You have 2 multiplied by y cubed minus 2 dx plus 3 multiplied by x y squared dy equals 0. For simplification, we will call it equation number 1. Now we know that the general form of the exact equation should look like mu dx plus nu dy equals 0, and equation number 1 is satisfying that form. Now we said mu is equal to partial phi over partial x. In this case, we have mu equal to 2y cubed minus 4. And in the meantime, nu is partial phi over partial y. Doing that will give us 3 multiplied by x multiplied by y squared. Now in order to have an exact equation, we said that partial mu over partial y should equal partial nu over partial x. Now let's testify. Partial mu over partial y, does it equal partial nu over partial x? Let's see. In this case, partial mu over partial y gives you 6y squared, and partial nu over partial x give you 3y squared. And of course 6y squared does not equal 3y squared. So the equation in front of us is not an exact equation. Now we want to try to make it an exact equation. So you will assume an integration factor. So assume an integration factor such that your integration factor should satisfy the following equation. So partial mu multiplied by integration factor lambda over partial y equal partial nu multiplied by integration factor lambda over partial x. Knowing mu and nu, we can compensate them directly in this equation. So we can say partial 2 y cubed minus 4 multiplied by lambda over partial y should equal partial nu, which is 3x y squared multiplied by lambda over partial x. Note that mu, or I mean the integration factor lambda, is a function of x only. So the integration factor lambda is not a function of y. It is a function of x only. Now, solving this equation, we can say that lambda multiplied by 6y squared equals lambda multiplied by 3y squared plus 3x y squared partial lambda over partial x. Now, knowing that, we can say that partial lambda over partial x equals lambda over x. From that, we can know that lambda equals x. Let's call this, let's just put it in a square, in a rectangle for now. So from that, you need to multiply equation number 1, which is the main equation we marked previously, multiply both sides by lambda. Now equation 1 prime, which is the equation number 1, after getting multiplied by lambda on both sides, will be 2 multiplied by y cubed minus 2 multiplied by x dx plus 3 multiplied by x squared y squared dy equals 0. So this is equation 1 prime. Now we said mu equals partial phi over partial x, which equals 2 y cubed minus 4 all multiplied by x. You can call this equation number 2. Now, if you integrate equation number 2 with respect to x, then you can say the integration of d phi equals the integration of 2y cubed minus 4 x dx. With that being said, now the function phi of x and y can equal to x squared y cubed minus 2 x squared plus g of y as an integration factor. Call this equation number 3. In the same manner, nu equals partial phi over partial y, which equals 3x squared y squared. So partial the mu x squared y cubed minus 2 x squared plus g of y partial y should equal 3x squared y squared. So in this case we can say 3x squared y squared plus g prime of y equals 3x squared y squared. Putting g prime of y on one side of the equation, we can say g prime of y equals 0. Integrating that, so after integrating g prime of y, we can say that g of y equals 0. I mean g of y equals constant c. So g prime of y equals 0. The integration of this part will give you g of y as a constant. Now, finally, the function phi of x and y equals x squared y cubed minus 2x squared plus c. And that's the grand solution of our differential equation using the exact method for a non-exact equation.